Good day to you. When organisms interact with their fluid environments, there are basically two fluids that they interact with. One is air, of course, and the other is usually water. In addition, there are a wide variety of different kinds of animal and plant shapes, ranging from fairly simple cylinders and spheres to quite complex organisms with lots of projections and appendages and various kinds of teardrop shapes and those kinds of things. Now, when you're dealing with that kind of diversity, you have to have some way of being able to make sense of the different ways or how those different shapes produce a particular kind of an interaction with the fluid environment. Otherwise, it could be just what Enrico Fermi called stamp collecting, documenting particular cases for particular organisms without having any kind of general feel for what's going on. Fortunately, there is a way for us to collapse some of this diversity into a fairly simple set of numbers that characterize the different ways that objects interact with fluid environments. And that number is, that quantity is something called the Reynolds number. And we're going to define the Reynolds number today and illustrate a little bit of the kinds of things that the Reynolds number can tell you. The first thing we want to do is we want to understand how an object interacts with a fluid environment. And so we start off with an object, and we have that object sitting in a fluid stream, and that fluid stream is moving at a certain velocity, and before it encounters that object, all the parts of the fluid are moving at the same velocity. But of course, when you have these fluid masses encountering a solid object, they can't go through it. They have to go around it. And so, if you look at the pathway that these parcels of fluid follow, they're going to tend to follow streamlines, and these streamlines will radiate. The distortion of streamlines will radiate out quite far from the object, like so. And what's happening when these streamlines are compressed at the lateral edge of the object is you're getting an acceleration of that fluid. That fluid is now going faster here than it was here before it encountered the object, and it's going faster here than it is down here when the fluid has flowed past the object. Now, by the rule of conservation of energy, the flow of fluid, if it has mass and it has velocity, is going to carry with it a certain degree of kinetic energy. But at the same time, there's pressure driving that fluid, and the pressure is going to come out as a form of potential energy. And according to the rule of conservation of energy, that is always going to have to be a constant. Now, kinetic energy is proportional to the velocity squared. Potential energy is related to the pressure. And when the fluid accelerates around the object, the velocity increases and the kinetic energy must go up, therefore. But this has to be a constant, and as it accelerates around, that has to be balanced by a reduction of potential energy there. And the overall result is that you'll end up with a distribution of pressure over the surface of this object over here, okay? And that is going to be highly positive on this end over here. It's going to be very, very strongly negative laterally on the lateral sides. And it's going to be slightly negative on the trailing edge over there. Now, what's going on here is that you are getting a distortion of the fluid that is coming about through the adherence of fluids to the principle of conservation of energy. This is a kind of interaction that we can call a dynamic interaction because it involves transfers of energy and conversions of energy from one form to another. And the famous Bernoulli's principle is one expression of this conservation of energy principle in the case of fluids. And so that's one kind of interaction that can take place between fluids and objects, these kinds of dynamic interactions that are involved with distortions of flow fields around objects. There's another kind of interaction, though, And here we want to look more closely at the surface of an object. And if we look at the parcels of fluid near an object, we can represent these as a series of parcels, and these are stacked up with respect to one another. The ones down here, close to the surface, these are subject to what's called the no-slip condition. That is, this fluid adheres so strongly to the object that it doesn't actually move. But then there's going to be a free stream velocity of the fluid far away from the object. And as you go closer and closer to the object, the velocity of these streams is going to go down, and you're going to get a velocity profile at the object that's going to look something like this. Now, the reason you get this velocity profile is you're getting a transfer of momentum from one parcel to another through the force of viscosity. And so this parcel will be held to this parcel by a viscous interaction, as will this one, as will this one, as will this one, as will this one. And if you look at how these parcels will be represented a short time later, you'll have one there, one there, one there, one there, one there, and this one will still be there. And all those are still going to be held together by viscous forces, or there are going to be viscous forces that are tending to hold them together. But of course, in this instance, you have shear forces operating, and the viscosity can't completely hold them together. There is some degree of slip, but the momentum doesn't go away. What happens is the momentum is transferred from the fast-flowing fluid down to the object. And the end result is that you end up with a force being generated on the object, pulling it forward. And this kind of interaction, that is a transfer of momentum through the agency of viscosity, this is a different kind of interaction. Whereas we spoke about dynamic interactions with the Bernoulli principle, these are so-called kinetic interactions. Right? That is, these are so-called kinetic interactions. The kinetic interactions are kinetic because they involve the transfer of momentum from one thing to another. So when you're talking about the kinds of forces that are operating on an object in a flowing stream of water, and this could be a still object in a flowing stream or a moving object in a still stream, you get these two different kinds of interactions with the fluid environment. The dynamic interaction that is embodied in Bernoulli's principle, and then the kinetic interaction which is embodied in the transfer of momentum through viscosity. Now, what this tells you is that there are really two different kinds of forces that are operating on fluids. There are, on the one hand, viscous forces that operate through kinetic types of interactions, but then there are other kinds of forces operating through dynamic interactions where the inertia of the fluid or the inertia of the object becomes very important. And one of the things that you can do to actually characterize the kinds of interactions that you get is to have some kind of a number that can express both the inertial interactions and the viscous interactions between the object and the fluid that it's in. And this is where our famous number comes in. This is known as the Reynolds number. It's one of the most fundamental numbers that you can use to make sense out of fluid flows. And the Reynolds number is quite simple in conception. It's usually abbreviated as capital R little e. And the Reynolds number is simply the ratio of two forces. An inertial force that is embodied primarily in these dynamic kinds of interactions between objects and fluids, over another force, the viscous force, which is focused primarily on kinetic interactions involved through transfer of momentum by viscosity. And these two numbers, they are both forces, and this leads to one of the interesting properties of Reynolds numbers, namely that the Reynolds number is a dimensionless number. Okay? Now, we can actually expand this a little bit because it's useful to see what goes into these different kinds of forces. And the Reynolds number can be described by a somewhat more complicated equation, but still quite easy in principle to understand. In the numerator, you have a term for the density of the fluid. This is kilograms per meter cubed. You have a length of an object, L, and how you define that will vary from object to object. And then you have the velocity of the fluid with respect to the object itself in V. This is over another term in the denominator, and this is the viscosity of the fluid, usually abbreviated with a mu. And this says a couple of things about the behavior of the Reynolds number. First of all, Reynolds number is more or less directly proportional to velocity. It's also directly proportional to length, and it's also directly proportional to the density. It's inversely proportional to the viscosity, however. So the larger the viscosity, the smaller the Reynolds number will be. Now, the Reynolds number is very useful for characterizing flows around objects. It's also very important in understanding the different kinds of fluid regimes that objects and fluids are subject to. And so, for example, if you look at the different kinds of flows that you can get around an object, one kind of flow that you can get is going to be so-called laminar flow, where you have nice, smooth streamlines of fluid flow going around that object. You don't have any kind of complicated departures of these streamlines from nice smooth lines. But you can also get certain kinds of flows that are known as turbulent flows. And if we look at the kinds of flows that are involved in turbulent flows, flows will come up and they will go around the object as it does in a laminar, in a smooth flow type of a situation. And then what will happen is you'll get eddies and those kinds of things, chaotic flows being generated downstream from the object itself. And those eddies are an example of so-called turbulent flow. And so if you look at the different kinds of flows that are possible, you have these kinds of flows right up here. This is laminar flow. And then you have these kinds of flows down here, which are known as turbulent flows. Now, one of the most useful things about the Reynolds number is it provides a common way of distinguishing the kinds of flow regimes that can lead to turbulent flow or to laminar flow. When you look at laminar flow regimes, these are typical of low Reynolds number situations. When you look at turbulent regimes, these are characteristic of high Reynolds number situations. And when we talk about high Reynolds numbers, we need to put some numbers on there. When you're talking about Reynolds numbers around 20 to 30,000 or so, that usually characterizes a transition from laminar to turbulent flow. All right? There's another thing that that is very useful in using the Reynolds number, and that is that it varies with body size. If you look at the Reynolds numbers of most organisms, for example, most large kinds of organisms that we're familiar with, then the Reynolds number that they typically experience in their fluid environments are quite high. If you look at the Reynolds number of a blue whale swimming through the ocean, for example, it's on the order of 200 million or so. If you're looking at a bird flying through the sky, you're talking about Reynolds numbers on the order of 20 to 50,000 or so. And so when you look at most large organisms, and this includes plants that interact with their fluid environments, you're typically talking about high Reynolds number situations. When you're talking about very small organisms, then you start getting down into low Reynolds number situations. If you look at a fruit fly flying around, for example, it's experiencing a Reynolds number of only about 100 or so. When you get down to small protists, like paramecium that you've seen in laboratory demonstrations, then those Reynolds numbers are on the order of about 0.1 to about 0.01 or so. And when you're talking about things down in bacterial size range, you're talking about Reynolds numbers in the 1 in 10,000th range. And so you're dealing with very, very small Reynolds number regimes there. Now, there's a very important thing to keep in mind about what happens as Reynolds numbers vary, and that is that Reynolds number is a ratio of the kinds of forces that are operating on organisms. And when you're talking about organisms that are operating at high Reynolds numbers, this says something very important. What it says is that what's governing their motion and their interaction with fluids is primarily inertial forces. when you're talking about how small Reynolds numbers explain how these organisms interact with their environments. Small Reynolds numbers characterize a situation where viscous forces are extremely important. And especially at low Reynolds numbers, because we're used to dealing in high Reynolds number situations, organisms that live in low Reynolds numbers are subject to a wide variety of seemingly anomalous and paradoxical kinds of interactions with fluids. For example, a small organism like a bacterium or a paramecium, those organisms have to, when they're swimming through the water, they have to be exerting forces continuously as they're moving from one place to another. They're moving through regimes, even though it's just water, they're moving through a regime where the Reynolds number is so low that it would be the equivalent of us trying to wade through hot tar. It's that kind of a difficult interaction. And if a paramecium, for example, stops running its cilia to move itself forward, it will come to a dead stop in the distance about the order of the diameter of a hydrogen atom. But on the other hand, if you're dealing with high Reynolds numbers types of locomotions, as is typically the case for large vertebrates and large trees and large whales, for example, there's an entirely different regime that's operating there. There, the inertial forces can operate so that, say, a whale that is swimming through the water only has to propel itself forward with its flukes intermittently, periodically. In between thrusts of the flukes, the inertia of the whale and the inertia of the fluids those inertial forces are sufficient to keep that whale going for a considerable period of time. And so just understanding the difference in the ratios between the kinds of dynamic forces that govern interactions between organisms and their environments, high Reynolds number situations, and kinetic types of interactions at low Reynolds number situations, you can go a long way towards understanding some rather strange things about the way organisms interact with their fluid environments. Well, that's all for now, and we will see you another time.